We're going to move on to the next speaker, and the next speaker is going to be Jason Hill, who's an associate professor at the University of Minnesota, and is going to be talking about some of his work looking at the life cycle analysis of biofuels.
Setting my timer, not checking my messages here. There we go. Thank you very much for inviting me to speak here today. In the previous talk, the issue of biofuels primarily covered greenhouse gas emissions, and what I'm going to do today is focus on air quality. And my reasoning for doing this is, of course, to showcase some of the new research we've done in this area, but also because it is a critically important part of this conversation about transitioning to next generation fuels. The Federal Renewable Fuel Standard, for instance, allows for additional fuel production if biofuels meet certain greenhouse gas reduction thresholds. But air quality, impacts on human health and well-being, impacts on water, impacts on food prices, et cetera, are only mandated to be assessed, not accounted for in whether or not fuels are indeed societally beneficial. And so biofuels have long thought to be one of the options, or have long been thought to be one of the options for clearing the air. Here is an advertisement from Clean Air Choice and from American Ethanol, showing that ethanol is indeed better for your family, cleans the air. But my group and I are interested in whether this is indeed the case. And this is because historically initial ethanol mandates were driven by reduction of tailpipe carbon monoxide emissions, add an oxygenant to the fuel, reduce the amount of carbon monoxide being produced. But much has changed since these initial mandates. Vehicle fleet has largely shifted from carbureted engines to fuel injected. We now know 90% of human health damage is from fine particulate matter, PM2.5, and ozone, rather than from carbon monoxide, which tends to be a more acute poisoning danger, and impacts of the carbon monoxide reduction mandates were largely based on fuel use, not on fuel production. So we put all these together. What sort of story do we find when we account for these other options? Just have to tell you a bit of air chemistry here as we go through this. We're looking at total fine particulate matter, which is the sum of primary fine particulate matter, primarily from combustion, as well as secondary fine particulate matter that forms in the atmosphere as a result of volatile organic compounds, sulfur oxides, nitrogen oxides, and ammonia combining in the atmosphere, as well as ozone, which forms as a result of volatile organic compounds and nitrogen oxides and light. So when we do life cycle assessment of different fuels here, this might be a little hard to see, but the first, it's almost impossible to see on this slideshow here. Let me see if I can just go to full screen. At the bottom, on the left-hand side of each of these, we're looking at gasoline, followed by gasoline hybrid engine. You have a better view than I do. Corn grain ethanol and corn stover ethanol. These are life cycle emissions, and you see in black in each case are emissions in production of the fuels, and in white are in use of the fuels. Now, you could dissect this in many different ways, but what I want to point out here is that if you're just looking at use, if you're just looking at the white part of the bars, you're missing all the emissions in the black part of the bars, the production emissions, which are very high for many of these pollutants, such as ammonia, sulfur oxides almost entirely, nitrogen oxides, et cetera. So you need to look at both production and use in these cases. The other thing I'd like to point out is this tells you a lot about how much of these pollutants are emitted, but it doesn't tell you anything about where they're emitted, where they travel, who's exposed to them, et cetera. So we don't care about that so much with greenhouse gas emissions because they're emitted to the atmosphere, long-lived, and have long impact, whereas some of these air pollutants affecting air quality, the impact occurs on much shorter timescales. So we have to do something different when we're looking at air quality effects. We need to create emission inventories, and these inventories need to be spatially and temporally explicit to understand those processes of formation and travel and exposure. From those emission inventories, we need to calculate changes in concentration and then exposure. ultimately health impacts, economic damage, and we can even go a step further and look at the environmental justice outcomes of these different options. I'll go through most of these today. I won't do the environmental justice options in the interest of time. Lifecycle assessment, and this is some other value added to our work, as I mentioned, is meant to understand the full life cycle of production and use of these fuels. So in order to do this, we need to look not only at the emission sources in the production of these fuels, but also where those sources are located, when they're emitting pollution, and so forth. So I want to tell you how we construct those sorts of inventories. We use the GREET model, which is from Argonne National Laboratory. Again, don't worry about all the details here, but the important thing you should be taking away from this figure is that we have a pretty good idea of where in the life cycle emissions are occurring for different pollutants, for different fuels. But again, this doesn't tell us anything about where, when, where they travel, et cetera. So we need to add some spatial and temporal descriptions to these different processes. And I'll run through some of these processes and what we did with them for you. Vehicle tailpipes, for instance. You see here a map looking at where emissions occur largely from vehicle tailpipes, largely correlates with vehicle mile traveled over the US. And you also see a temporal description up there as well at the bottom over the course of the year, as well as an average over the course of the day. You have two peaks on that there on the bottom left, corresponding to the morning and evening rush hours. Next map, ethanol plant evaporation non-combustion emissions. We looked at the location of where these facilities would be located. You need coal to produce electricity in many of these, for many of these fuel options. So we looked at where coal is mined and cleaned. Fertilizer, where fertilizer is used. Over the course of the year, fertilizer is used, and emissions of ammonia over the course of the day. Gasoline refineries, sulfuric acid production, which is actually a major component to phosphate fertilizer production, largely in Florida. So you take all these processes, and we literally have hundreds of these processes in the life cycles of these fuels, and you add these spatial and temporal descriptions, and you layer them one over the other, and you can produce cumulative inventories here for the US of these different pollutants. So I'm going to show you two here that are somewhat different. VOCs on the top for gasoline, corn ethanol, or Stover cellulosic ethanol. And you notice there, sorry, my timer went off. You notice there that these largely correlate with tailpipe emissions in urban areas. But then look at the cumulative emission profile for ammonia, the bottom three maps. For gasoline, corn ethanol, and corn cellulosic Stover ethanol, not surprisingly, this correlates very highly with the production of corn in the Midwest Corn Belt. So what I'm going to do now is tell you a bit about a study that my co-authors Chris Tessum and Julian Marshall at the University of Minnesota and I published in Proceedings of the National Academy of Sciences last December, looking at the human health effects of different life cycle emissions of these fuels. We considered 11 light-duty transportation options, everything from conventional gasoline engines to hybrid engines, diesel, compressed natural gas, a number of biofuel options, current and potential, as well as electric vehicles with electricity produced from different sources. We modeled scenarios for 2020 in which 10% of vehicle miles traveled were replaced by one of these options and looked at the overall health impact from these different transportation options. And what I want to do now is show you some of the results of that. So from our baseline scenario in A, we have the 12 different options looking at the change in average annual PM 2.5 from those different options. We have gasoline there in B, gasoline hybrid engine, again very similar, but lower emissions because you're using the fuel more efficiently. Diesel, this is a pre-Volkswagen diesel emissions I might add here. Compressed natural gas. Corn ethanol in panel F. You can see here large, high concentrations in the Midwest, and a lot of which also drifts to the east. Corn Stover ethanol, you notice emissions there, some reduction in emissions in some coal mining areas. That's due to displaced electricity from the production process, which offsets some coal electricity production. electric vehicles grid average in H, electric vehicles coal in I, there's one giant blob of red over the eastern 2/3 of the US, electric vehicles natural gas, corn stover, and electric vehicles wind, wave, and solar. You can also run the same exercise as we did. It should say average ozone concentrations at the top rather than PM2.5 concentrations at the top. This is all changes in ozone. Fairly similar maps arising from that. So from these changes in concentrations, we can combine this with exposure with population data from censuses. And calculate, based on dose response curves, average changes in mortalities per year from this 10% replacement and from ozone and PM. And then we also broke out the striped part of the bar is PM2.5 from battery production. I won't go into that now, but there's a lot of interest in the effects of battery production on air pollution. And what we see here, of course, is that overall mortality is dominated by PM2.5 rather than ozone, consistent with many other studies. And we see, we can actually on the bottom axis relate these overall deaths using a value of statistical life to damage per gallon of gasoline equivalent of these fuels. So essentially, the way to translate this is burning a gallon of gasoline damages human health and well-being to the equivalent of 50 cents a gallon. Corn ethanol, you see the fifth bar down, is about twice that overall. So much more damaging in terms of air quality. Electric vehicle, corn stover ethanol, since this is a biofuels talk, next in our modeled scenario of 10% replacement would be about equivalent to gasoline in terms of damage. And then you can see in the electric vehicle options, there's a wide range everywhere from the grid average, which is higher than gasoline, similar to corn ethanol, EVs from coal, which are incredibly damaging, down to renewable sources like wind, wave, and solar, natural gas. And even notice on wind, wave, and solar that because of the infrastructure, there are still some mortality and damages from that as well. Of course, we can also localize this. This is some maps we developed looking at where those deaths occur on the average year. And of course, these are average statistical deaths rather than deaths that we can sign off on a health certificate. Sorry, on a death certificate. Very different things. A death certificate for. And finally, I just want to close showing what this would look like in terms of estimated changes in greenhouse gas emissions from this gold standard GREET model as estimated by them compared to the damages that we see from air quality. And this is interesting. In some cases, we see that certain interventions, like moving to gasoline hybrid engines, not surprisingly, reduce both the effect on climate change and air quality. Others, such as corn ethanol here, again, this is not including indirect land use change, as was mentioned in the last talk. In that case, it might be a slight reduction in overall climate change impacts, excluding land use change, but much worse in air quality. In some cases, things are consistently bad, electric vehicles from coal, for instance. And in some cases, like electric vehicles, wind, wave, and solar, you're making things much better, not surprisingly, on both an air quality and climate change basis. So anyway, I guess what this is meant to show is that we need to go a little further if we're going to understand the true impacts of these fuels beyond the sort of traditional analyses that we do just to quantify the amount of pollutants released. If we're going to look at pretty much anything other than climate change, we need to understand where, when, and have some sort of sophisticated modeling to understand how those impacts occur over space and time. So with that, thank you very much.